This video discusses several operations on matrices, specifically scalar multiplication, addition and subtraction, linear combinations, and equality of matrices. You'll notice throughout this video that our matrices are not augmented matrices. Since we're not solving systems of equations, we don't use an augmented matrix. It's just going to be a regular matrix. Starting with scalar multiplication, any matrix can be multiplied by a scalar quantity. So this means no matter what the dimensions of the matrix is, we can perform this operation. And a scalar quantity is simply a real number. When performing scalar multiplication, you're going to multiply every element of the matrix by the scalar out in front. I think of it as just distributing the number in front to every element in the matrix. We want to multiply this matrix by -5. We're just going to multiply every element. Don't make it hard. We get -20, -45 in our first row, +15, -35 in our second row. And that's our answer. That's it. When adding and subtracting matrices, the two matrices have to be exactly the same dimension. If you're asked to add matrices that aren't the same dimension, then you say, I can't perform this addition. What we're going to do when adding or subtracting is that we're simply going to add or subtract corresponding elements. And corresponding elements are elements that are in the same position of each matrix. Our first example is addition. The first thing I note is, yes, my matrices are the same size. And our answer is going to be the same size as those matrices as well. Now all we need to do is add corresponding entries. So we're going to add 1 and 13. That gives us 14 in the first row, first column. Next we'll add 7 and 8. That's 15, first row, second column. And now we'll add -9 and 4. That gives us -5 in our first row, third column. And we'll do the same for our second rows. Adding the numbers in the first position, we get -1. In the second positions, that's -13. And in our last positions, adding those numbers, we get 2. There's our answer. Make sure you wrote that 13. It didn't show up the first time I wrote it. Right. In the next example, we are asked to subtract. And it is true that we subtract corresponding elements. However, I think that can be hard to keep track of, like especially if we're looking at the second row, first column, -2 minus a -1. Well, that's really -2 plus 1. Personally, I'm afraid I'm going to lose track of all those negatives. So what I like to do is the same thing that I do with polynomials. I'm going to distribute the negative into the second matrix, and then I can just do addition. We do that when subtracting polynomials. We distribute the negative into the parentheses and then combine like terms. I personally prefer to do that so I don't make a mistake with all those negatives. So I'm going to turn this into a plus and then change the sign of every element in the second matrix. And now we're back to the problem we just did. We're going to be adding corresponding elements. Note that our matrices are the same dimension. And our answer is also going to be 2 by 2. So we're adding 3 with -6. It's -3. 0 with 4 gives us 4. negative 2 with 1. It's a negative 1. And lastly, 8 plus negative 7, positive 1. And there's our answer. Our next operation is called a linear combination. Basically, this operation combines scalar multiplication and addition. Since this does involve addition of matrices, two matrices have to be exactly the same dimension in order to perform a linear combination. This is written slightly differently. So here I've said let A be equal to this matrix and B be equal to this other matrix. And then I'm asking you to find negative 3A plus 4B. That is the linear combination. So I'm just going to rewrite this by putting the actual matrices in place of the A and the B. So this is negative 3 times our matrix A, and I'm going to write it out, plus 4 times our matrix B, all right. Well, order of operations rules the math world even when you're performing operations on matrices. So think about it. What do you think we're going to do first? The scalar multiplication or the addition? We're going to do the scalar multiplication first. I'm going to multiply into each of these matrices. Negative 12, negative 15, 6, 0, negative 24, positive 15. I'll do the same with the second matrix. I'll distribute in that 4, 12, negative 8, 16, negative 4, 0, 28. And now we'll simply add corresponding entries. Negative 12 plus 12 is 0. Negative 15 plus a negative 8, negative 23. 6 plus 16, 22. 0 plus negative 4, negative 4. Negative 24 plus 0 is negative 24. And 15 plus 28 is 43. Here's our answer to that linear combination. The last operation we're going to look at in this video is the equality of two matrices. Two matrices are equal if their corresponding elements are also equal. That makes sense. If they're equal, well, then they're equal. Of course, two matrices have to be the same dimension as well to be equal. So here I have a matrix equation. I have one matrix equal to another matrix. We are going to solve for the variables within that matrix using the fact that corresponding elements are equal. So we are going to set corresponding elements equal to each other. We have negative x is equal to 3. 2y equals negative 6. 3 equals 3. And x plus y equals 4z. Now we solve each of these equations. If negative x equals 3, then x is equal to negative 3. If 2y equals negative 6, then y also equals negative 3. 3 equals 3. Notice that there's no variables there, so there's nothing to solve for. And yes, indeed, we have a true statement, so that's good. They should be equal. Our last equation is a little trickier. X plus y equals 4z. we're going to substitute the values that we have found for x and y into the equation and then solve for z. So had you written that equation down first, you would have had to solve the other ones before you could solve this fourth equation. So -3 plus -3 is a -6 equal to 4z. Dividing both sides by 4, and of course simplifying our fraction, we get -3/2 is equal to z. Since we are not solving a system, we do not need to write these answers as an ordered triple. This is just it.